All right, so we get started here. So we left off last week. We're talking about two population examples where we had proportions. So we've got some Excel stuff that we're going to do. But just kind of as a reminder, we're going to work through an example just to kind of get refresh our minds about what we were talking about. So let's say we had this example where we had, I think we looked at this survey before, whether or not people were in favor of healthcare coverage for everyone. We had two different time periods. So we had sample sizes from both time periods. We also had kind of these sample proportions that we found. So what we wanted to know was there a difference between the 2011 and 2010 kind of views on ensuring everyone or healthcare coverage for everyone? So kind of mentioned when we have these time period examples, always use your newest time period first. So kind of think about this as 2011 will be our group 1, 2010 will be our group 2. So if we want to know which one of these hypothesis tests we're going to be using, same kind of thing as one population examples. Anytime we see this word different than, automatically we're thinking we have this two-tailed test, right? We have a not equal to sign. Now I also mentioned that we're always going to use the assumed true difference no matter what type of example, whether it's means or proportions, we're always going to use 0, right? So another way to think about this is, when we think about what this difference is, so it's the difference between 2011 and 2010. So if we want to know whether or not they're different from each other, the only way, right, if they're different from each other, that means they're not equal to each other. Whereas if we want to write this out in terms of the difference of these two things, if I do a little bit of algebra here and subtract 2010 from both sides, I'm really saying, is this difference not equal to 0? Right? And that's what I want to test for. So that's my alternative hypothesis, which means the null, I assume the exact opposite is true, which is that it is equal to 0. Right? So I've got this as my kind of null alternative hypothesis. I have a two-tailed test. Right? So the next step is, let's try to find these critical values. So anytime we're dealing with proportions, right, one or two population, if we have proportions, that's the standard normal or the z-tables. Right? So we want the critical value for an alpha of, well, if it's the 1% significance level, alpha is 0.01. Right? So we have two tails. What we're thinking about there is we've got this difference between the 2 years. We're assuming it's centered around 0. And we want to find, for a two-tailed test, we'll have a pair of critical values such that alpha total is in the tail, or alpha over 2 is going to be in each tail. Right? Alpha is always going to be the area that's in your tail. I always say it's the area that's in your, you wrote it out, kind of like you're reading it. If you have one tail, it's the area in your tail. If you have two-tail test, it's the area in your tails. Right? So equally sized tails, so alpha over 2 on each side, or we have alpha of 0.001, 0.005 on each side. So let's go to our table. Now I'm going to use this t-table because it's kind of a little bit easier. Where if I want 0.005 in that tail, to get the z value, I just go down here to that last row because I know that if the degrees of freedom for a student t distribution was infinite, that is the same thing as a standard normal distribution. So I can get it out to the third decimal using this table. So positive and negative 2.576, right? I have this pair of critical values for the two-tailed test. Well, I'm not thinking right yet. So positive, negative 2.576, sorry. So we've got these critical values now. We just want to kind of keep going with our example here. And we want to know, okay, my rejection region is kind of anything more extreme than those critical values. So I kind of draw those arrows in the tail. And if my test statistic falls in those regions, I can reject. So the next thing I need is my test statistic. Right? So from here, it's just going to be a matter of, and once I'll get that kind of third formula sheet up once we go through all these equations for the final exam. But it's really just a matter of identifying what test statistical equation we need. But we're dealing with proportions, right? So we know we're looking for the difference in those proportions. In the last class, we mentioned that we're doing something a little bit different when we're dealing with proportions because we have an assumed true difference, but we don't have an assumption for what the true population proportion from group 1 and the true population proportion for group 2 is. We're just assuming the difference is equal to 0. If the difference is equal to 0, those two could both be 0.8, they could both be 0.4, we don't know. So in order to ensure that our test statistic is coming from a standard normal distribution, we have a slightly different kind of equation. So we'll plug in our sample sizes, plug in our sample proportions here, get this intermediate step of calculating p-bar, so 0.83, plug that in, plug in our sample proportions, plug in our sample sizes. That assumed true difference we had was, remember, 0. So that kind of just goes away. So we plug everything in, we get about 0.92, right? So we failed to reject the null hypothesis, but why? So if we have 0.92 as our test statistic, oh, I forgot my marker. Where would that kind of fall? 0.92, that was our z statistic or our test statistic. Clearly not kind of in that rejection region. So we failed to reject at what? This was the alpha of 0.1, so the 99% confidence level, or at the 1% significance level. In fact, if we were to do every single level, the 10, 5, and 1% significance level, we'll find that with this test statistic that's less than 1, that's pretty small, it's not going to be in the rejection region for any of those. Okay? Any questions on that? What if I had wanted to find the p-value? So the p-value would be the probability that I saw the test statistic that I did, or something that was as far away from that assumed true difference of 0, or anything further that went against the null hypothesis. But for a two-tailed test, if I only take one sample, it would have been equally as likely for me to see something that was, say, 9.2 standard deviations below that assumed true difference, or anything further. So really, my total p-value is going to be kind of the area in both these tails. So once I find this guy, right, I have to multiply by 2. Okay. How can I do that? Well, I can go to the table, look up 0.92. It'll tell me the area to the left. I want the area to the right, so I could then subtract that from 1. Right? So if I do that, let's look up 0.92 real quick. It's a test statistic. Actually, technically, right, I think if we round this to the third decimal, we should be looking at what, 0.93. So 0.93. So 0.93. The area to the left is 0.8238. Right? So we plug in 0.8238. Whatever that ends up being, that's our p-value. So what? Something around 0.34, it looks like. Probably just below that. Okay. Or just above it, actually. Any questions on that? We're good? Okay. So let's see how we do this in Excel. We'll also kind of review how we do confidence intervals. So we go back to this two population HT blank file. Remember, we had kind of male, female, total undergraduate enrollment. And then I created this variable, which was, does the school have more female students than kind of male students, right? So it's a 1 if they do. So in this case, right, they're more female than male students. Down here, this school has way more male students than female students, right? So that's a 0. So I could think about finding the sample proportion. Well, we said when we have a 1, 0 variable, if we simply take the mean of that, that's essentially going to reflect to us a sample proportion. It's going to count up the number of 1s and divide it by our total sample size. So it'll be the number of schools that have more female than male students, right? Or the proportion of schools that have more female than male students. So we'll take the average of this variable. So we get about 0.85. Sample size, use that count function. That just counts up the number of observations we have. And then I also want to do this for my other sheet, which had Midwest schools, right? I had 2 samples here. I'm looking for maybe, I don't know, is the kind of proportion of schools in the Midwest that have more female students higher or lower than those in kind of the South. So I already had these calculated over here. So all I have to do is equal sign, click on that sheet, click on that cell, hit enter, and it kind of puts that reference that I'm looking at a different sheet here, right? And nicely enough, I actually have the sample size right below it. So if I just copy this down, it'll update that cell reference and grab the cell that was below it on the other worksheet. Right? So now I've got my two sample portions and my two sample sizes. So I can go ahead and I can actually find confidence intervals here. Right? So if I'm trying to find a confidence interval, right? If we go back to last week, and kind of, well, let me see, I can actually pull that up. So we go back to last week. Let's see where we're at. Somewhere like right here. Nope. I just want the equation. Here we go. This is going to be the equation that we want, right? So it's just a matter of entering this into Excel, clicking on the cells that have these sample portions and sample sizes in them, and then finding that Z value that gives us alpha over 2 on either side of that confidence interval. So if I know kind of the area in the tails that I want, the way that we do that is we're working in reverse or working in inverse, right? We know the probability. We want to find the Z value that gives that to us. We said we could look up kind of alpha divided by 2. Now, the only issue here is that's always going to give us a negative value. Once we enter the lower and upper bound equations in there, we just want to keep using kind of this absolute value of the z-score. So we'll use that ABS function, right? So now this should give us that same value, but positive. We'll copy this down so we can have the Z value we need to build the confidence level at the 3 different alphas that we want, right? These kind of correspond, kind of if we were following up here, right? Whoops. Just going to copy these, paste them just as a reminder. The 90, 95, and 99% levels. So I copy those down. So I'm going to put in my lower bound equation. Well, the statistic that I'm building my confidence interval around is kind of the difference between these two proportions, right? So we'll do South minus the Midwest. I believe that's how we set up the mean examples as well. Maybe not, but for the sake of what we're doing here, kind of do South minus the Midwest, right? We'll then subtract our margin of error, which is the number of standard deviations away we want to go, multiplied by the standard deviation of this statistic we're interested in, which is the difference in sample proportions. So the way we get that standard deviation is it's the square root of, say, the first group's sample proportion times 1 minus that sample proportion divided by that group's sample size. Okay. We then add to that, right, the other group's sample proportion times 1 minus that sample proportion divided by that group's sample size. Okay. So all I did here was enter that equation into Excel, and I also use Excel to find that Z value. Okay. Now, if I'm copying this down, I don't want anything to change for the other confidence levels I'm building, or intervals I'm building, except for the Z value. So everything else, I can highlight this. You can Command T on a Mac or F4, or if you have an FN key on your laptop, FN F4. We'll kind of put dollar signs around all those cell references for you, so you don't have to kind of go through and do it all by hand. Now if I copy this down, notice it keeps using those same sample sizes, sample portions. It only updated the cell reference for the Z value. Okay? So if I then want the upper bound equation, I basically want the exact same thing, but I just need to change this minus, right? I'm not subtracting that margin of error, I'm adding it. So I'll just copy this, so Control C, go over to the cell that I want to paste it in, and change that negative sign to a positive sign. So the only difference in my lower and upper bound equations. Now I copy this down, and I've got my 3 confidence intervals. Now notice here, right, all of these confidence intervals are all kind of, one of the possible values is 0. So, based off our confidence intervals, one of the true values for this difference could in fact be 0, or that there is no difference, right? If the difference is 0, we're saying that they're the exact same thing. So we go ahead and do a hypothesis test, but this is a pretty good indicator that probably 0 is going to be something we probably fail to reject as a true difference. Now it's a little bit different because here we had 2 sides mattering. If we do a one-tailed test, that can change things a little bit, right? Because we're only concerned with kind of one side of that distribution. So I have kind of this null alternative hypothesis over here. I think, well, what do I want to do here? So if between the south, so I'll determine what the, I can't remember how I had it set up in the answer key. I think last week we did a right-tailed test. So let's say we want to know if the South minus the Midwest, maybe we want to see test for whether or not the Midwest has a fewer proportion of schools that have more female students, right? So we want to know if we look at that difference between the South and the Midwest, is it, well, actually, no. I think I had this set up. I probably don't. Let me make sure this matches up with the complete file I posted. I don't want to go through and do this so that it doesn't match. Okay, so I did flip the confidence intervals. I apologize for that. So what I wanted to do here was, just so we can make sure it matches up with the complete file, it doesn't matter how you define it. It would just change kind of, well, I'll show you. So notice here we got like negative 0.01, 0.03, 0.07, 0.22, 0.24, 0.28. If instead I want to define this as not the South minus the Midwest, but instead the Midwest minus the South, and you'll see why I want to do that here in just a second, just to kind of make the English a little bit easier. All I'm going to do is change the direction, right? So I'm going to take the Midwest minus the South here. Once again, I don't kind of want those to change, so I'll freeze them. Right? Copy this down, do the same thing over here. It's okay if you don't want to go through and change these on, if you're working through with me, that's fine. But they're just going to look a little bit different in the complete file because I did define it differently. So notice it's the exact same values. It's just now the upper bounds have become the lower bounds but negative, and the lower bounds are now the upper bounds but positive, right? That's just because we changed the direction of which group we were subtracting from the other. And most of the time it doesn't really matter which group is number 1 and which group is number 2, because you're still finding, right, the same range of values. It's just going to be a little bit different in how you describe it, right? Now, instead of saying, if I look at kind of the South minus Midwest, the only possible, most of the possible values were positive. So if I look at the Midwest minus the South, now most of the possible values for that difference are going to be negative, right? Because I'm just flipping that around with how I'm saying it. So we're going to do this as the Midwest kind of minus the South, right? So we're going to say, is that difference, Midwest minus the South, maybe I want to test for whether or not the proportion of schools in the Midwest that have more females and males is in fact lower than the proportion of schools in the South that have that, right? So I'm looking for, is that difference, right, Midwest minus the South, is it negative, right? So I'm going to have a left-tailed test, right, because last class we did a right-tailed test, so I want to make sure we work through a left-tailed test example. So if I'm going to calculate my test statistic, the first thing that I'm going to do, right, is calculate this p-bar. So if I go back to the equation, all p-bar was the sample size. It's kind of like a weighted mean. Take each sample portion, multiply it by its sample size, and then divide it by kind of the total number, right? Add up those 2 sample sizes. So sample proportion from group 1 times their sample size. Add to that sample proportion from group 2 times their sample size. Now that was my numerator, so I'll put that in parentheses. And then divide by kind of the sum of these sample sizes, so this sample size plus the other group sample size. That gives me that intermediate p-bar value. So then to get my test statistic, I'm just going to kind of continue out, get this formula entered into Excel. Right? So I'll take, the difference in the Midwest and the South's sample size. Now I could do here, subtract the assumed true difference. It doesn't really matter if I do that, if in fact that assumed true difference that I'm using is 0, because subtracting 0 isn't going to change anything. But just for the sake of completeness, we'll put it in there. I then divide by the square root of, where's P bar? Oh, it's right above here, so it's gonna be hard for me to select. Hold on. I don't know why it does this. There's gotta be a thing I can turn off. Oops, I didn't want to do that. So it's in what? Cell S22. So take P bar times 1 minus P bar, multiply that by 1 over first group sample size plus 1 divided by the second group sample size. Okay? So whatever cell I have that P bar in, take the P bar times 1 minus P bar, and then multiply that by the sum of 1 over each group sample size. Okay? Oh, did I forget a parentheses? Yeah, I did. Yeah, just throwing a, so I just clicked yes, so it threw an extra parentheses there for my denominator. Okay? So I should get about negative 1.5-ish here. Okay? So if I want my p-value for a left-tailed test, thinking about, I found this test statistic of negative 1.48. I want the probability I saw a test statistic that far away from the assumed true mean or anything further that goes against the null. I have a one-tailed test now, so I don't have to multiply anything by 2. So now the area in that left tail is my p-value. So I've got this z statistic, or my test statistic that comes from a standard normal or z distribution. I want the area to the left of it. The function in Excel, it's the same as what we were doing for the two difference in sample means, right? Equals norm.s.dist. You tell it, here's my z-value, comma 1. That gives you the entire area to the left, which is exactly what we wanted. Right? So I've got a p-value of about 0.07. Okay? So if I'm making my rejection decision here, I could even kind of throw that in. I can type. Right? And kind of say, okay, if this p-value is less than my alpha, comma, if that's true, put the word reject, because that's, if that is true, that's when I should be rejecting. Comma, if it's not true, put in the word fail. We could put in fail to reject, but I'm just going to shorthand it here. Okay? So we can kind of see this all in one line. Now, when I copy this down, I want to compare to different alphas if I want to make rejection decisions at different significance levels, but I want the p-value to stay the same, so I'm going to put dollar signs around that cell reference. Okay? So I copy that down, and it kind of makes sense. P-value is less than 0.1, so I reject. It's not less than 0.05 or 0.01, so I fail to reject at those levels. Right? But at the 90% level, I could say that I can reject that the difference in these proportions is greater than or equal to 0. Or what I could say there is I could reject that, in fact, if this was positive, would have to be I can reject that the Midwest has a higher proportion of schools than the South that have more female students than male students, right? So we do see some difference across the Midwest and the South in regards to this specific, variable, which is kind of interesting. I have no idea. I mean, probably we kind of have to explore why that might be the case. But it is kind of interesting there, right? So we could also find critical values. It's a left-tailed test, so automatically we know these critical values are going to be what? Positive, negative, pairs. It's a left-tailed test. We know critical values are, negative, right? Because what we're thinking about is, what critical value would give me alpha in the tail? Well, we're looking at alphas of 0.1, 0.05, and 0.01. Well, we know the area to the left of the mean is 0.5, and our mean is 0. So it is way less than 0.5, so we're going to have to be getting a critical value that's negative. Right? So now we're kind of working in reverse, just like we were with confidence intervals, where we know the area we want in the tail, and we want to find the z-value, which is now kind of this cutoff z-value, or a critical value, that gives us that area in the tail. So we're, once again, working in reverse or inverse. Well, now it's actually a little bit easier because we just want alpha in that left tail. So we're done, right? And we kind of copy this down. You can kind of see this test statistic, right, would be kind of passed, right? If we're looking at the left side of the distribution, we actually want a test statistic would have to be like a larger negative value or larger in absolute value. So it's larger in absolute value at this kind of 10% significance level, but not at the 5 and 1, right? So same decision we would make kind of with that p-value approach, okay? Any questions on this one? All right, and I'm not gonna go too in detail with this, but like, because I'm not giving you examples where we do this. But let's say I want to test against something other than 0. Let's see how I set this up. So actually, I'll do this just so it's a little bit easier. Let's say I want to know if the kind of difference between these proportions is anything like, I don't know, less than 0.05, right? So I want to check against a different value, right? Well, I can actually plug that in and it'll update everything for me, right? So I can kind of test for whether or not, make different rejection decisions about what this kind of difference is. I don't have to just use 0, but for the sake of everything I'm going to be showing you, just to make it a little bit easier, I am going to be using kind of 0 in every case. Okay. So here's where I decided to do this because I was reading this morning and I saw something that was interesting. So before I do anything, any questions on any of that, or how we would kind of want to see a cell again, or make sure I see this. Okay. Make sure no one's waiting in here, by the way. All right, we're good. So I saw this thing today, and let's call this, so I want to know if the F, so I set this up like this. So let's do Moderna here, Pfizer here. Pfizer reported that they had a 90% efficacy rate on their vaccine, and I saw Moderna posted, or I don't know if they posted, they announced today theirs was 0.945, right? The sample size from Pfizer I was looking at was like 43,000 people. However, I think of the people that got it, they had 90 people get it, and 90% of those 90 were had the placebo, right? So that's how they were kind of reporting this efficacy rate. I have a hard time saying that word. I think Moderna reported 94, and like only 5 of the people got it, right? So we could kind of test for like whether or not Moderna is in fact performing better than Pfizer based off of kind of just the people that we've seen get it. So we kind of go through this. We can't really say that kind of Pfizer's is, if we think about this difference, we can't say that in fact it's where we can't reject the fact that Moderna's is better, right? So we're assuming kind of that difference is greater than or equal to 0, right? We go through kind of all this and we fail to reject at every level. So we can't really say that what Pfizer's is worse because we're failing to reject that null that the difference is in fact greater than or equal to 0. So if we're thinking about this, can't really say, based off of kind of the sample evidence here that, Pfizer has a less effective kind of vaccine than Moderna based off the sample size we have. Now, that's thinking about the people that actually got it. But they're actual samples of people. So this is where I'm not a good enough like biologist or chemistry person because they gave out like 30,000 vaccines. So I don't know, if we're thinking about the sample sizes there, this is kind of the proportion of people who got the disease, who had the vaccine. You really want to think about how effective this vaccine is. We would need something about like exposure rates and kind of how much of that sample was even had an exposure to the virus. But kind of just based off of the people that got it and those who had the placebo, we kind of go through to a test like this, right? And I was thinking about this because I was thinking about which one of these companies should I buy stock in, right? Because if this vaccine ends up working, right, someone's going to make a lot of money. So, but once I had this set up, like once I have a left-tailed test set up here, if I have all my cell references, yeah, I mean, obviously, like this is my original data, but if I was grabbing kind of, having sample proportions that I already calculated and I had the sample sizes, I can just plug them in here and it just automatically tells me what my rejection decision should be. So, which, on the Excel assignment probably means this is a pretty good template to how you should set up your Excel assignment, right? Okay, so that was a little bit of an aside there. We're going to start going through now kind of the more realistic scenario when we're looking at the difference in sample means, which is we don't know the population variances, right? I have to go through these examples because there are some situations in which they apply, and it is kind of a better place to first understand before we move on to the situations where we don't know the population variances. But the more realistic scenarios are we only have sample variances, right? So remember, with one population, what do we have to do differently? When we only have sample variances, that was the time where we had to use the student t-distributions. Right? And we said there's actually several student t-distributions. There's one for every single sample size or every single degrees of freedom. So our degrees of freedom before was n-1, right? So we're going to do things exactly the same way as when we had the difference in sample means and we had population variances for the confidence intervals. It's just that we use sample variances instead of population variances now. And instead of using a z-value that gives us alpha over 2 in each tail, we're looking at a different distribution, so we need to use the t-value. But structurally, like, nothing's changed, right? And we've had some practice with one population examples about how to look up this kind of t-value. Right? Now, the one main difference, and this is where I'm not going to make you guys do a lot of this work, so I'm going to show you something and don't freak out, because I'm not going to have you do this. But instead of n-1 being our degrees of freedom, I'm calling it delta here. Okay? And the reason why is because if we have two different samples, the distribution of each one of those sample means will depend on the sample size, right? Because for different sample sizes, they'd have different degrees of freedoms and would be coming from completely different student t-distributions. Before, we didn't have to worry about that because each sample mean was coming from a standard normal distribution, right? Or at least, sorry, was coming from a normal distribution, which we could then kind of turn into the standard normal distribution. Well, now we have different sample sizes. We're looking at completely different student t-distributions. So how do we find our degrees of freedom, or how many do we have? All of them, because America. Anyways, it's actually going to be using this equation, which looks nasty and is really hard to get entered into Excel sometimes. I mean, you've got a lot of parentheses going on. But notice, I mean, it's really just taking the sample variances and sample sizes of both groups, and we're kind of doing a little bit of work to ensure that we're using the correct student t-distribution, or we're selecting the correct degrees of freedom. Okay? Now, I'm never going to have you guys use this, right? In fact, on your Excel assignment, do I have it on this file? I think I do, or on this file, on this USB Excel 4. I might not. I can pull it off of Canvas though real quick because I want to show you this. Yeah, I must not have put it on here. So let me go to Canvas real quick. Files, I think it's under. So here's this fourth Excel assignment. So let me download this real quick so I can show you what I'm talking about instead of just saying. I think saying will make a little more sense. So you'll see these cells right here, like they're angry because I don't have any values in yet. Well, basically, I don't know, I'm just going to make up some numbers here right now. Oh, why didn't it like this? Probably because these don't make any sense. So let's do 25, 35. There we go. Let's say I had some sample means and some sample variance I calculated. Once I calculate my sample sizes for these two groups as well, this function is exactly what I showed you on PowerPoint. Like I said, when you put this into Excel, there's a lot of parentheses in here, right? So this is something that's very easy to make a mistake. Just visually, it's hard to make sure I have enough. So I've got it already entered into Excel when you download that file for the homework. So don't delete those. Like when it just looked like this, don't delete those, right? I have those in there so that once you do the work here, it automatically will spit out at you what the degrees of freedom should be. Okay? Now, when we use that equation, you know, it could very well be that I don't get an integer value, which is a problem because degrees of freedom are all integer values, right? So if I did get like a, I don't know, 83.9, it doesn't matter. I won't just round it. I'll always round it down. So 83.9 will become a degrees of freedom of 83, which is kind of like erring on the side of caution because remember, as we move further, like higher degrees of freedom, we get closer to that standard normal. So we're going to make sure that we're kind of like essentially making it harder for us to reject. Right? And that's built into the that's built in here too. So this was the actual equation. And then there's this function in Excel, which is floor, which is like always round down, even if it's 83.9, make it 83. And that's already kind of there in Excel for you. So once you get your work done, you'll have the correct degrees of freedom here. And the one that you'll be using to find t-values will be this one that's already been kind of rounded down or floored down. Okay, so what are the kind of the steps? Well, identify the pieces of information we need, sample sizes, sample means, and now instead of population variances, sample variances. Now we also need alpha, and to find kind of what t-value now, because we only have sample variances, gives us alpha over 2 on each side of our confidence interval. We use this crazy equation. You guys aren't going to have to use this. I'll kind of always give you an assumed true degrees of freedom. In fact, I'll double check the Connect homework. I wanted to make sure there's none in there that where you have to calculate this, where it should always kind of give you that assumed true degrees of freedom. So I'll make sure I go in there today and review that. And if there's anywhere you have to calculate it, I'll put an announcement on Canvas that just gives it to you. Because this is just this is an exercise in really how good are you at using a calculator where you won't make an easy mistake, right? It's kind of difficult. So once we have that degrees of freedom and our alpha, find the t-value, and then it's just a matter of plugging and chugging, right? It's the same thing we had before. We've got our components that we need. Once we have that t-value, we're essentially just plugging those values in. Okay? So let's go through an example. Let's say I'm kind of interested in, is the response time from people who are texting while driving different than people who are not texting while driving? So I said NT here is people who are not texting. Text is when people were texting, right? So you can kind of see my sample size of people who are not texting, a sample size of people who were, the differences in the mean response time. Notice like non-texters, it's a kind of lower value, which means it's a quicker response time. It's kind of weird, like when we say quicker, that really means it's a lower value. When I have kind of my sample variances as well, so if I'm building this 90% confidence interval for non-texters and texters, what the true difference is, well, I'll base that confidence interval around the sample difference I found. So non-texters minus texters, so 1.3 minus 2.36. So I'm thinking about, this is what, 1.3 minus 2.36. So negative 1.06 is what I'll be building my confidence interval around. Right? Okay, so if I look at these options, I didn't give you options. So if we kind of saw, if I had this set up as like a potential question, anytime I saw a confidence interval that didn't include that negative 1.06, I know that can't be a possible option, right? Because it has to be exactly in the middle of my confidence interval. But at that point, it's just a matter of identifying our piece of information. We had the sample sizes, sample means, sample variances. If I wanted to do did I freeze this? There we go. If I wanted to do a 90% confidence interval, my alpha is 0.1, but it's a confidence interval, so I know that I have alpha over 2 on each side. So 0.1 divided by 2 is 0.05. My degrees of freedom here, I'm going to have to plug them into that equation. So let's say, like on a test or something, what I would tell you is assume the degrees of freedom is 80. Right? Now that I know my degrees of freedom and the area I want in the tail, which is 0.1 over 2, 0.05. Oh, not that one, this one. So I've got my degrees of freedom 80. Got to find the column I want, which was 0.05 on each side. So 1.664. So now that I've got that t-value, I had everything else, just a matter of plugging things in. Right? So here, I've got my lower bound, and here's my upper bound. Right? So negative 1.33, and negative, I think it was 0.79, or might have not. Negative 0.79. So with 90% confidence, what can I say here? Well, if all these values are negative, what I can say is that true difference for the mean response time between texters and non-texters, the only possible values can be with 90% confidence, I can say that it's a negative value, right? Or that it's less than 0. But what's the only way that this difference is less than 0? If this is the larger value. So with 90% confidence, if I rearrange this, I can say that the response time of texters while they are driving to non-texters is actually higher. They're taking longer to hit the brakes, basically, right? So, these are interesting questions that, if we have some sample data, we can get a pretty good answer to. And then, so if you could stop texting while driving, that'd be great. I remember one semester, this is an aside, but I did this example and I said, I shouldn't preach because I think I did this the other day, and I had someone that was so so horrified, and in the middle of class, not chastise me, but they were not happy. But look, this is a hard thing to stop doing, right? It's a bad habit. So, I think this is a good example where we didn't have before, where if you have a confidence interval that's all positive or all negative values, that gives us some power to say some really interesting things about the example. If it ever crosses over where you see positive and negative values, that means zeros in there too. So the true difference could be that there is no difference. Maybe finding no difference is interesting, but more often than not, kind of these examples where we're only on one side of 0 are the more interesting ones. Okay. All right, where are we at on time? Let me think about what we're going to do Wednesday and how I want to end class here. So I'll review this one just a little bit. We'll go through it a little bit quicker probably. So if you want to kind of review this on your own, or if you have any questions, make sure you kind of ask me. After class ends, I'll kind of hang around. But, let's say I've got different cigarette brands and I want to know whether or not the nicotine levels are different between the two. So I sample 20 of the one brand, I find the sample mean and the sample variance, sample the other brand, find the sample mean and variance. What would be the 95% confidence interval for the difference between brand A and brand B, right? So I'm going to be taking kind of brand A minus brand B. So right away, I look at what am I going to be building my confidence interval around? What's the difference I see in these sample means? Well, 1.68 minus 1.95, so it's what, negative 0.27? So I know negative 0.27 has to be exactly in the middle of my confidence interval, right? So if I look at these confidence intervals, which one can I rule out right away? B for sure, right? They're all positive values. I'm building it around a negative value, so that negative value has to be in that interval. I can also rule out A, because I found negative 0.27. Negative 0.27 is not in between these two, right? So right away, I've got this kind of boiled down to these two. And now it's really just a matter of, I've got the piece of information I need. The 95% confidence interval, my alpha is 0.05. But I have half of alpha on each side of my interval. So I want 0.025 on each side of the interval. And I told you, assume the degrees of freedom here is 42. Right? In fact, if you work it out, I believe that is what it ends up being. I'm not just making that up. So we go here. We want 0.025 on each side of our interval. At degrees of freedom 42. The t-value that does that for us, 2.018. So now it's just a matter of, 2.018, it's just a matter of plugging everything in, right? Kind of get our lower bound, get our upper bound. Once again, we have a pretty interesting example here where, with 95% confidence, I can actually say that brand A, right, has a lower nicotine level because we set it up as brand A minus brand B. So they're all negative values. So I can say that with 95% certainty, brand A has a lower amount of nicotine than brand B, right? Which if I'm trying to, I don't know, if I work for a cigarette company and I'm trying to make sure that my product has, if I'm selling it as though it has higher, this is important to me if I'm brand B, because this this is backs up my claim. And if I'm brand A, I got problems, right? If I'm claiming that and then I go out and I find this, Another kind of thing to think about here is I can say this with 95% confidence. What happens if I want to say it with 99% confidence? my interval is going to get wider, right? If I want to say something with a higher level of confidence based off the same sample data, then I'm going to have to include a wider range of values. Now, my guess is if we did that, this is still pretty far away from 0. I'm doubting that if we redid this and used the t-value that gives us not 0.025 in the upper tail, but at the 99% level, it would be 0.01 divided by 2. So 0.005 in each tail. If we rework the math, we're so far away from kind of 0 for our upper bound here, the 99% confidence interval probably doesn't overlap 0 either. But, if we were closer, we could rework that and make, double check and make sure we could say this with 99% confidence as well. Okay. All right, I think we'll stop there for today. We'll kind of pick up on Wednesday how we do these hypothesis tests when we only have sample variances. We'll also work through an Excel example for confidence intervals and hypothesis tests for these situations as well. And then Friday, we might even start kind of going over some of the problems on Wednesday about matched pairs. We'll for sure kind of finish up and see how we do matched pairs in Excel by Friday as well. And once we get there, that's everything you'll need to kind of complete both the Connect and Excel assignments. But up to this point, you have a pretty good amount where you could get pretty far through the Connect assignment and at least work through the first kind of half probably of that Excel assignment, okay? All right, if you guys have any questions this week, feel free to email me. I'll talk a little bit more Wednesday about what classes are gonna look like kind of after we go to Thanksgiving break. Other than that, I'll see you guys on Wednesday.